All right. So yesterday, at some stage, when we were analyzing this matrix, we manipulated that term that appears there in the harmonic approximation. We could write it that way, and this one we wrote like that. Okay, I forgot about these two terms. Okay, fine, but let's include those now. So when I include those, I can write it in the continuum limit like something like that. And tau is related to that kappa alpha beta that appears there. Okay? So the equation of motion is here. Given the Lagrangian, you know how to derive an equation of motion now, right? It's the Euler-Lagrange equation. Now, you make the Fourier decomposition. The Fourier decomposition, essentially, you have to include that. Okay? Once you do that, see what you find. You find that minus omega k squared plus k squared is equal tau squared. Okay? And then omega k squared plus tau squared. You recognize that expression there? Energy squared is equal to the momentum squared plus something. In particle physics, what is this quantity here? It's the mass. Okay? Mass. So what is the conclusion? Conclusion is that this Lagrangian here, when I quantize it, it has quanta, okay, with a mass m squared. So these are particles, massive particles. In the case of photons, this term was not there. Okay, now this is there. Okay, how about the units here? H bar and C. This is, I'm working in the H bar equal 1 and C equal 1. Okay, I can put them back when I come here, put 1 over C square here, and then I get the dimensions correct. Okay. It's just tau. Thank you. Or I put a tau square there, such anyway. Okay? So what have you learned? Oh, I read almost everything I'm telling here, but it's just that the quanta of a quantized field, right? They are particles, massive or not massive. How do I account for different particles, different fields? This is a scalar particle, okay, because the field is a scalar. So it doesn't have spin. How about the electron? It's something similar, okay, but I need another field that carries spin, okay? I don't have time to talk about the Dirac field, okay? But once I have spin 1/2, then this is a spinor field, is not a scalar field, okay? Anyway, the photon, the field is a vector, and a vector has spin 1. A graviton will be a tensor field, okay? And so on and so forth, okay? But the basics is this thing here. So this is the canonical quantization. Canonical quantization is you get the field, expand in Fourier components, and put a hat on the creation on those ladder operators on the Fourier components, and then you recognize that this is the harmonic oscillator, and then you get this. But you remember that I had other terms, say K alpha, not K, I forgot the letter I had there, but I had terms like that. When I make this continuous, this goes to phi cube. Now, we'll add a term here, say 1 over factorial of 3. Don't worry about these numbers. You will see later why. Lambda phi cube. Okay. Now, the equation of motion will include another term here that is not linear, is not phi, it's quadratic here. Fourier decomposition is not suitable here. Why? Because you want the linear superposition, okay? And when we have phi here, different Fourier components get coupled, and this is not useful anymore. This is an interacting theory. This is when you have such a thing there, you have an interaction between phi. You know that phi is essentially decomposed in creation and annihilation operators. Phi cube will give terms, say, A dagger, A dagger, A. So what is that? It annihilates one particle and creates two. Annihilates one, creates two. And vice versa. Okay, so the interactions are included in terms beyond quadratic. When you quadratic Lagrange, this is a free field theory. It's an harmonic oscillator. Beyond quadratic fields, these are interactions. Okay. So this is the canonical quantization. Let's look now at the path integral. Powers beyond square. So this, and then you have, say, 1 factorial of G by 4. So there are these interactions here, and so on and so forth. Okay. Phi 6, 3 body interactions. Path integral. This is a different way of quantizing. Instead of putting hats, we will do something different. Okay? And just to motivate that. Yeah? To be renormalizable, right? This has to have up to some power. I perhaps get to that. Okay? So you cannot have arbitrary powers here. Then the theory is not renormalizable in the old sense. In the modern sense, in the effective field theories sense that I will explain on Friday, you have to die here. Okay. So the integral, let's start with quantum mechanics. This is also copied from Z. Okay. So Z is a book that you must have. Okay. If you come to particle physics or field theory, you will learn a lot during your 5 years here, say, just to calculate things. But for the interpretation, it's good to have something else. And Z's book is for that. Okay? So suppose you have a source here, and then you have a screen, and here is where you collect the particles. So it comes here. By now you already know that the amplitude, okay, the amplitude of detecting the probability amplitude to detect the particle here is what? Is the amplitude passing through this hole 1, and so the probability is the square of that. Okay? I think you know that, right? Fine. So there will be interference here, okay? Is it an interference here between coming through here and coming through here? Now suppose you make another hole here. What will happen? The particle can pass also here, and it can come here. Then you have to add a 3 square. If you put another hole here, or you have to add all the amplitudes for passing through each one. But now, suppose you again have this, you have some hole here, and you detect it here. Okay. It can come through here and here. Suppose you put another one here. Okay? Here and here. Okay? But you cannot, you might have actually not here precisely that. You can have it here and here, say. So this comes through here, or can come here, can go there, and so on and so forth. Put another one here. What will happen? This will go through, depending on where you put the holes. Now suppose you put infinite things here. Infinite screens here with holes. And more than that, you don't make only 2. Make a continuum of here. Continuum of holes here. What is the picture you get at the end of the day? See if you agree. So the probability from here to reach here, what is it? Is it something like that? It might be. What can be this? Where this comes from? That imaginary screens that I put here. Okay? It can come through here. It can come through here. So in quantum mechanics, to calculate the probability for a particle starting here, reaching here, you have to add over trajectories. In classical physics, there is only one. This one, say. Right? Given the initial conditions, there is only one path. Now, in quantum mechanics, you have this possibility. All of them have a probability associated to each of these trajectories. Okay? And I have to add all of them, otherwise I get a wrong answer. You got the picture? That is the idea of quantization, path integration, that you have to add all paths to get the probability amplitude coming from here, reaching here. Okay. This comes with the name of Feynman, but Dirac has it already. Feynman visualized that, and Dirac only made the mathematics before that. Okay. So the amplitude, you have to add about over this. But what is the value, the probability amplitude for each path of that? And that is the tricky part. Now you have, this is only talking, right? Now, what is the probability of coming through here, coming to here, coming to here, or here, or here? Okay, let's evaluate that. You know what is that, right? This is solution of the Schrödinger equation when the Hamiltonian is time independent. Okay, is the evolution of the state vector from a time t to a time t prime. Okay. Now we can write this in the coordinate representation. So this gives a wave function psi q prime t prime equal the integral over dq k q prime t prime minus t psi q t, and this object here is q prime e to minus h okay. It's nothing. It's just project here in q prime, put q prime here, okay, and then put a complete set of states here of q. So to have this q here and the q, right? Because this is q, the psi of t. The same here is q prime, and then you get that. Okay. Excellent. Now what Feynman has shown in Dirac is that this matrix element here, integral, a functional integral I s of q. And this is the classical action. It's amazing, isn't it? You want to evaluate this object here? It comes with the Hamiltonian. And at the end of the day, to get this object here, you have to sum. Sorry. You have to add. This is a strange object. Okay. The meaning is these are the trajectories that you have to add. It's a generalization of simple integrals. I will explain how to get there. Okay. But this is the answer. So if you have a classical Lagrangian or you have a classical Hamiltonian, find the Lagrangian from there. Once you have the Lagrangian, you get the action. It's just to integrate over time. Exponentiate it in this way and integrate over all possible trajectories connecting from time t to t prime, because this involves an integral over time. Okay, you integrate over all trajectories from the initial time to the final time. Okay, and you get the quantum evolution of the system. Okay, this is called the Feynman propagator, or kernel, or whatever. Okay. So how to evaluate that? It's all done in full glory in my notes here and in many books. Okay, I will simply show the main steps. Someone asked me yesterday, what are you supposed to answer Saturday and Sunday? Okay, I will tell by the end of this lecture. Okay. So don't get too nervous. Essentially, what you do is the following. Call this T. Okay. So then you have, say, this is T. the time interval. Then you divide it up in small bits. So e to the I h t. Okay. So this then is, say, a delta. This is an epsilon, such that this n times epsilon. Epsilon is delta t. Okay. When you divide it up here in bits, equally spaced, say. Okay. So then you can write this as you agree? Because epsilon plus epsilon plus epsilon blah 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 is t. Okay. Now I do something here that you don't like. Well, this is still okay. Right? This is fine because it's the same operator there. Okay. So here, then I have this string of products. Okay. And what I do, I insert in each of these complete set of states of Q. Say. Okay. At each part here, each of these, I include the Q. So what is the advantage? Thing is that I have then, in each of those bits, I have Q, J, say, E to the minus I epsilon. You know it's called, shit. Anyway, epsilon H I. Okay, because there is one K coming from here. Okay, K is here, but here is Q. Sorry, it's a Q. Q here, and another different Q here, right? Because this has another integral here. Say the Q. So say this is 1, 1, 1. This is 2, 2, 2, and so on and so forth. So they are different. Okay. On the left, this Q is different from that Q. Okay. And now I do something. Which is to write this as J. T. Let's write it like K. Okay. The Hamiltonian is kinetic energy plus potential. So, is this safe to do this what I have done? Why? Because this doesn't commute in general with that. Okay? But what is the difference between this term and this term? You have to, you expand this out, and you will see that the difference here, E epsilon H, is equal. I don't have time to show this in full detail. The difference between this and this is a term that goes with the cubic power of epsilon. So if I divide this in sufficient small bits of epsilon, at the end of the day, I will take this equal to 0 to get the continuum again, right? So I'm safe in neglecting that. Okay? Very well. Once you do that, okay, you can show that at the end of the day, I have shown this here for you, okay? Now I'm evaluating, because this is a function of q only. Let's make the assumption it doesn't depend on time and velocities. Okay, so this can be, I can act it here and simply can put this out here, right? Because this is a function of q, so this is an eigenstate of the q position operator. Put it out, and I have to evaluate only this. And this one you can easily show. How can you show this very easily? Put a p dp here. Okay, put it here. Okay, this is the operator. When it acts here against the number, and then you perform the integral. At the end of the day, you get m 2 pi epsilon 1/2 I m over 2a Okay, what is that? If I do this epsilon and put epsilon square here, I can take this epsilon, put it inside here. So I have the difference between two neighboring points divided by that. What is that? The derivative with respect to time. So this is the velocity. Okay. So then I get here the velocity. I started with the momentum because this comes from the Hamiltonian, and end up with a velocity square. So then I traded momentum by velocity. You see the roots of the Lagrangian appearing? Okay, I have momentum, end up with velocity. Okay, that is the root of coming from the Hamiltonian, getting to the action, to the Lagrangian. Anyway, at the end of the day, you get the following. This k, q prime, q, t prime minus t is equal m 2 pi I epsilon 1/2 many times, okay, integral dq1 to qn minus 1 exponential I m over 2a 2 epsilon okay. So I do the trick here, put an epsilon square here, but then I have to multiply by epsilon here, okay, and epsilon here, epsilon here. So this term has an epsilon there, and this term has an epsilon there. Okay, so when I add up all these things, what is that? Is the integral of kinetic energy minus potential energy. Okay, so the steps are done here, then you do it, and at the end of the day, you get the result I advertised. Plus I, okay? Plus I. You see how it goes. Not the details. Don't pay attention to the details. Details you will have 2-3 years to figure that out. Okay, but just the idea. Okay, I want to calculate that. At the end of the, you see that this makes sense. Okay, because I started from here, separated this axe here, I put it outside. Okay, and then you have to evaluate that. That is given by that. Okay, then you put all bits together. Okay, and you end up with this e to the I. So I something, okay, kinetic energy minus V. Okay, I here because this is minus. Okay, so K minus V is the Lagrangian. Okay, and the integral comes because of epsilon. It's the Riemann integral, right? Basis times height. So what is that funny object? You see all this thing here? All this I'm telling you here has to do with the exponential here, okay? But you still have to integrate over all this. So this is the funny you see how many integrals? So each of those goes to minus infinity to plus infinity, okay? These Q values. Because you put the complete set of states can vary from minus infinity to plus infinity. Okay? So this Q here then means all these integrations here. Okay? So this is the measure of the integration over different paths. So this is one path, a path, and so on and so forth. So I'm integrating all that, and I realized sure I had there with these screens there. Okay. So then I have And this symbol here means this. So in practice, how will you use that? You have to just, well, never say you have to. But the practical way of doing that is always to discretize in this way and make the integral for the problem you are interested in. Okay. In practice, you can solve it for the harmonic oscillator, for the free particle. You can do all this analytically. For the hydrogen atom, it's a bit more complicated. Okay. So this is not very practical to solve quantum mechanical problems that we solve the canonical Schrödinger equation or Heisenberg's equation of motion. But it's extremely helpful in quantum field theory, as I will say. So how to quantize a classical system? In this way is you have the Hamiltonian, find all at the classical level, you see? There are no hats here. Okay. You have a classical Hamiltonian, find the classical Lagrangian, you get the action, put it here. There's an H bar missing here, okay? There's no what? No hats. No. Hats is inside here. That is the starting point. When I started from the Schrödinger equation, this operator has a hat. Okay. Now, this is to derive that. So this is the final result. Result is this. So if you want to quantize a classical theory, this is the final result. This is okay. You have to get the action and you get that. There are no hats here. How come you can have quantum mechanics just from classical objects? Where is the quantum mechanical thing entering here? The sum over different trajectories. Not only one trajectory here. It's not only the classical equation. It's not only the equation that satisfies the equation of motion. Can I see the classical solution here? Yes, I can. Suppose H bar goes to 0, which is the classical limit. This thing will oscillate like hell because it's I over 0 is infinity. So this oscillates a lot. Okay, if I change Q a little bit, this will oscillate like crazy. With the exception of one of them. Which one? That one, that S delta Q is 0. When I change Q, S doesn't change. Okay, I change a little bit Q and S doesn't change. But what is that? Here I get the Euler-Lagrange equations. Okay, so this is the classical solution. So when H bar goes to 0, H bar goes to 0, the only solution that makes sense here is the classical solution. So you get the classical solution from quantum mechanics, which is okay, right? Because classical physics is the limit of quantum mechanics. Right? Now you already know what I'm getting to now with quantum field theory, right? What is the difference? Notice these Q's here are functions of time, okay? All these are functions of time here. To do such a path integral is very instructive for the free particle, okay? I don't have time to do that, okay? But it's an exercise that you are not supposed to make on Saturday and Sunday. Fine. How about field theory? Remember the mattress? So this was for one particle. If I have many particles, I have to repeat this for each particle here. Okay, is a Q1 for particle 1, Q2 for particle 1, Q3 for particle 1, Qn minus 1 for particle 1 times Q1 particle 2, blah, 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 and so on and so forth. And this increases like hell. Okay. No hope to use Riemann integration here and things like that, okay? That you have learned numerical simulations. Okay? To use Monte Carlo methods here and things like that. Fine. So field theory. Yeah? What you do? That. So this thing here, when I have many particles, this is dq of particle alpha 1, blah, 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 dq particle alpha n minus 1, and so on, and you have to make the product over alpha. Because you have many particles now, you have to repeat this for each particle. Okay. The Hamiltonian here in the top here, this will be for one particle, you have to sum over all particles. Now, when you go to a continuum from many particles, like from that matrix, you see alpha goes to the integral in 4 dimensions, like that. That clear? Yeah, you already know that. Yeah? So, essentially, in field theory, this object, okay. Here I have a little bit better explanation, okay. But the object that is similar to this one, and which is useful in field theory, is this thing here. Instead of Q, you will have what? Phi. Instead of alpha t, like I have there, I have x and t. E to the I over h bar s of phi. S of phi is the action. And that's the way you quantize the field theory. Instead of making creation and annihilation operators, you have paths, okay, over different field configurations that will you have. Each of these paths is a configuration for particle positions. Okay. Now, when you generalize this, these particle positions are now fields, so are different field configurations. And you have to sum over all field configurations. And the classical equation of motion comes from delta S equal to 0. Euler-Lagrange equations for the field. But the quantum theory, you have to add over all of these objects. Okay, and then we use here a number. We call this Z. Not because of Z. Because this is a partition function, it's an analogy with statistical mechanics. Okay, and L of phi 1/2 phi square minus phi. For a scalar field, for example. You have questions? You see how it comes. Not the details, okay? You should not care much about the details. Ideas, how you make it, okay? Then you make quantum mechanics 1, quantum mechanics 2, quantum field theory 1, quantum field theory 2. There you do this, all the details, yeah? Yeah, it's here. Yeah, I will show you how you get to that through another object that is called the propagator, which is K. Hold on. Yeah. Alpha is d3x because t is still there. T is still, so this is 3. Yeah. D4 because I already had a dt there, sum over alpha. So this goes dt, d3x, so this comes from this. Yeah, from here. I have to sum over different alphas now. And the discrete sum over alpha is the integral. Oh, sorry. That was your question, right? Sorry. You know, I want to get these things through, and then I get. Okay. So what is the aim of all of this? Is for you to be able to calculate a correlation function, to calculate that scattering amplitude. All this fuss here, if you knew quantum field theory, I will not be doing that. I will do immediately the calculation of the scattering amplitude. So this has a double aim here, is to tell a bit about effective field theory and field theory itself. So it will not be complete any of these two objects. But anyway, you are here just to ask ideas, right? Okay. Now, let's start with a non-interacting field theory. And think about particle physics, okay? So the Lagrangian, 1/2 delta phi square minus 1/2 m square phi square. Okay. Remember, this is the phi dt minus phi square. I'm working with h bar equal 1 and c equal 1. Okay? And I will consider this object here, z of j. Not exactly z. What is the difference? Difference is I'm coupling is an external source that I included there. It will be a trick. It's like when you have studied statistical mechanics, remember the Ising model? Remember when you have magnetic systems, you have the spins, SI, SJ is here, but then you couple an external magnetic field, B times S. So this B is J, this is phi. It's an external field that you couple linearly to the field. Why I do that? This is a trick to calculate correlation functions. Okay? Next. Now, I want to evaluate this. Let's make this path integral. This I can do analytically. Again, I will do it in hand waving. How you calculate a path integral is what I said before. You have to discretize this system. Okay, so what I will do, I will take this phi here. You don't have to be very specific. Just have the idea what is going on. Which goes, I will replace this for a phi on a site, which is phi I A. So I have x that goes to I A. It's like this. You have now space, you have discretized space and time. And this is A, or AS. Okay? Doesn't matter. A. Okay? So the field now is defined only here, 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 here. It's like before I had time. Remember, I have discretized time. Now I have discretized time and space. So the field will be defined only here, 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 and here. So what happens? The derivative will go to 1 over A, I plus 1 minus phi I. Because I need the derivative here, you see? Inside here I have derivatives. Okay. And I will write this as 1 over A sum over J M I J phi J. So this is a matrix that has essentially 1 and minus 1 and zeros. Okay. This is essentially a matrix that has zeros here, 1 here, and 0 here. Okay, because of this, you see? Only first neighbors. Diff for X. You see, I'm going back to the matrix. This is field theory in the continuum. I'm going back to the matrix. Okay, I'm discretizing it. Before I came from the discrete system to this one. Yeah, I is the same for time and space. Suppose you divide it equally the same. Since C to 1, both have the same dimension. Yeah, right. So I is, this is 1, 2, 3, 4, 5, 6, blah, 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 and so on and so forth. Then you have to keep track in your computer. This 1 here actually means I, J, K, end of the T. It's a mess. But here, just conceptually. Okay. That is good. Theoretical physics. Don't go to the practice. So what you get? Z of J then is equal the limit in this matrix, limit of when n goes to infinity. See if this makes sense. If phi 1, phi n, I over 2, sum I j, I, m bar j, plus I sum so this bar here, m bar and j bar, they absorb a factors. Yeah, because it's full of a's here, okay? So put these a's inside m and call it that. At the end of the day, you have that. You agree? Or not? This first bit here, okay? This bit here includes this part and that part, okay? I have to put the m square here inside too. Dash. Okay. Now you have to put m square, phi square, and this goes to m square phi I square. So this term plus that term, you can write it where m bar absorbs all factors and m. Then I can write that thing like this. Okay. So at the end of the day, I get this thing here. So this has the derivative, which is this term here, plus m squared phi I squared. That is also included here, right? When the phi squared is when this is 1. So from the derivative, this has zeros here. Is of this. And from the mass term has only 1, 1, 1, 1 here. And 0 here. So this is m bar. This is the structure of m bar. But you don't know to need any specific thing. Yeah? Huh? Okay. Is that clear that the structure I get is that or not? If you don't understand that, then you are lost. Okay. The discretization here, this is like a matrix. I can write in this way here. Okay. You can simply see that because if this is, say, 1, if you have phi I plus 1 minus phi I, so you have only, if I is 1, for example, this is 2. So it's phi 2 minus phi 1. And this you can get multiplying this by a matrix L, M1, 2, phi 2, 1, I. Okay. And so what is M2, 1? So when I is equal to 1, when it's 2, this is 1, and when this is 1, this is minus 1, and so on and so on. You can write this as a matrix. All right. So this is a multidimensional integral. You see here, this is a multidimensional integral, but it's quadratic. You see here, it's quadratic. Have you ever done such integrals? You have done one of, like this one. Integral minus infinity plus infinity dx EIX squared plus BX. Actually, you have done something with that. Huh? How you do that? You complete squares. Okay. You complete squares, and then you get here the square root of 2 pi. Well, then if you put a 2 here, so this gives 2 pi over a 1/2 b squared over 2i. Okay. Now you have many integrals here, and they are coupled to each other. Okay, because you will have an integral, say, one of the terms is I m 1 x1 squared. That's great, but there is another m1 2 x1 x2. You see, the coordinate x1 is coupled to the x2. So how you do such integrals? Okay, there's a trick here. You have to diagonalize this matrix, but you do it only in your head. You diagonalize this, okay? So then you get integrals of this form here. Okay. Only diagonal elements appear. What are the diagonal elements of a matrix? Eigenvalues. So you essentially get products of eigenvalues. What is the product of eigenvalues? Determinant. So the answer is the details you can find elsewhere. The answer is minus 2 pi I n. Where is the I coming from? Because of the I here. One over square root of the determinant of that matrix times E 1/2 of J I M bar minus 1 I J J J. Okay. Where this term comes from? It comes from that term that have E B square over A. Remember? 1 over A is the inverse of the eigenvalue, the inverse of the matrix. Okay. And B square is J times J. But since this is a matrix, you have a repetition here, and that is the answer. It's done here. Okay. Does it make sense? Okay. Since I started 5 minutes later, I still have 5 minutes. Is that okay? This is just a multidimensional integral, okay? It's nothing. Now I take the continuum limit. Okay? I go back to the continuum. But the important message is the following. Only this part here depends on J. This depends on J. This doesn't depend on J. You see? Only the determinant of that. So, this object that I have defined here is what? Is something that goes from constant here, okay, constant with respect to J, okay, times exponential I over 2 integral d for x d for y j of I. Now, is the inverse of the matrix that appears here. What is this matrix here? It's made from the derivative and from the mass term. Okay? I will call that matrix D. dx minus y j y. You see, this is the continuum limit of this result here. Okay, because this is sum over ij. Okay. Remember, bar has all the a factors inside, such that this ends up in an integral. The integral is there. Okay. And what is the inverse? This is the inverse of what matrix? I had it there. Phi, I had that. Okay, this I have to do now, tomorrow. Okay, to show that this is actually, I can write it as 1 over d square plus m square. Okay, because it is the inverse of that term here. I integrate by parts here, then this gives minus 1/2 phi minus 1/2 m square phi square. So this is minus 1/2 phi delta square plus m square phi. And integrate by parts, put away the surface term. Okay, I imagine a localized system, and then I get that. So this is the matrix. Includes the derivative, which is this term, and the mass term. So this D is the inverse of this matrix. Okay? And I show you to calculate this inverse next time, tomorrow. And then we are almost done. Because here to calculate correlation functions now is like that. Questions? Too much stuff? As I told you, you have to get the ideas. Okay. First, the quantization of a classical field goes not through putting hats, goes through summing over paths. And the probability amplitude of each path is e to the I over h bar s, where comes from. I flashed here how to calculate that. Then you have to integrate. And the integration, you do it going back for the free field theory case, coming back to that, and you get the result. Now I will use this z of j to calculate correlation functions, including the scattering amplitude, which is the exercise you are supposed to do to understand matching conditions and all that. And all this will be done tomorrow.
Any questions?
So in the the point particle case, the path integral that we wrote had the very clear meaning of the transition between the particle being at some point and later at some other point was given by a restriction on the paths that we were considering under the integral, right? When we go over into the field case, are we doing it between different configurations of the
Different
field?
configurations, so different, because different trajectories are different configurations, right? There's different ways the particle can propagate. But now the variables are not positions of the particle. The variables are phi, are the field variables. Okay, so different field values, they define a configuration. For example, the field is some in a, say in something like that. This is one configuration. But it can be also another configuration. Imagine this a field here, like you have to add all these field configuration. This is a function of x and t. You have to add over all possible. And the weight, the importance of each of those is given by this factor here. Okay. So from here I have to calculate correlation functions now. It's one step.
Anyone else? Then let's thank Gastão again. And we have coffee break and we'll be back at 11, I guess.